Let us now look at the kinds of forces that we need to deal with. One very important force is what we call the gravitational force or weight. I'm going to use both of these as the same term. Okay, so gravitational force is the weight. If an object has mass m, it has a force of m into g. G is the acceleration due to gravity. Now, generally I'm going to assume g is 10 meters per second square, so this will be 10 times the mass. So for example, you usually say that you are 50 kg, right? So you say, what is your weight? You say 50 kg. That's not right. Actually, your weight is 50 into 10. 50 into 10. So you are 500 Newton weight. Your weight is in newtons. Your mass is 50 kg. So we all know our mass. Actually, our weight is 10 times whatever we thought. Okay. So weight is the force with which the earth pulls an object. So let us take this. This is one important force. So if I had an object, this object has a force of mg. Let us say that this particular object has 7 kg. It's a 7 kg object. There is a gravitational force of 70 newtons. I am assuming in this case that g is 9, not 9.8 but 10. Sometimes you might have to use 9.8 looking at the question. I am just going to assume g is 10. So for all this, let us assume g is approximately 10 meters per second square. So this is one kind of force. Every object on the surface of the earth is going to have this force. The second important force is the force that with which I am pushing objects, right? Contact force. Now we split contact force into two pieces. We say contact force consists of one part which we will call normal force and the second one which we will call friction force. Now if I look at this board and I take this, my finger, and basically I push. Now I am pushing it in this direction, right? Part of what I am doing is to push like this, partly I am pushing like this. It's a combination of two forces. We will talk about normal force. I will use the symbol small n. Why won't I use capital N? Because I've already used it for Newton. And then friction, which we will generally use F. I will come back to friction a little later. It's an important force, but it's a little complicated force. So we'll worry about that later. Normal force is a very simple force. So for example, if this thing was kept on a floor, the floor is going to push it vertically up because it's perpendicular to the surface. So the floor pushes this object with a force N. Now this force may or may not be equal to 70. In this case, it happens to be 70. Sometimes it won't be. Like for example, if I keep this chalk piece like this, let us say this chalk piece was 1 Newton. Force, weight was 1 Newton. Okay. Now this chalk piece is at rest. Gravity is pulling it down, 1 Newton. Normal force, that is my hand is pushing it up, 1 Newton. But if I start to lift it up with an acceleration, so suppose I start doing that, when it is going up, then the normal force is more than that 1 Newton. Okay? So normal force can be equal to 70, can be greater than 70, can be less than 70. What is normal? The word normal in English, just simply old English, used to basically mean perpendicular. So normal means perpendicular. That's all. It doesn't mean anything special. Normal does not mean normal, regular. It's not that kind of normal. It is perpendicular. So for example, if I took this object and I placed it on a floor, the force is perpendicular. If I had an inclined plane and I kept this fellow there, what is perpendicular to the inclined plane? This way. So normal force will act like this. Normal force will act like this. So if I am standing on the floor is pushing me up. That force is the normal force. Okay. So we are going to deal with this. Now for weight, I know the value of the force. If I am 100 kg, my weight is 1000 newtons. If I am 50 kg, my weight is 500 newtons. So what is my normal force? Is there a formula for that? No. We need to find normal force from the problem itself. Okay, we will learn how to do that, but I hope that is clear. Every time I am pushing something, it is normal force. If I punch you, I am exerting a force, contact force. Part of it will be friction force, but a large part of it will be normal force. Okay, you punch me back, you are exerting a normal force on me generally. Now it may not be normal, because if this force was not like this, it was like that. This has two components, one like this, one like this. This force we call friction force. This component of the force we call normal force. So normal force is not this entire force. This is friction, this is normal. So what is normal force? The part of the contact force which is perpendicular to the surface, that's called normal force. Okay? How big is normal force? However big you need it to be, unless the object breaks. So you take a table and you hit it hard, huge normal force. You jump up and down. So when you hit the floor exerts a very large normal force on you. You take a ball and throw it, or you throw it on the wall. When you throw it here, the ball bounces because of a normal force. So normal force is everywhere. Okay. Now the third kind of force that we are going to deal with is what we call tension force. If I had a rope and I pulled an object, so for example, if I had a block and I pull this with a rope, suppose there was a rope and somebody is standing here, okay, and so they are basically pulling this fellow. How do you pull? How do you exert a force here? I take this rope and I pull, right? Now this rope we say is under tension. So if the rope is tense, it's taut, tight. Okay. Now we say that it has a tension T. Then we are going to deal with light ropes. So we will call it light as in very, very massless. Okay, light massless ropes. So right now we'll only focus on this. So whatever I'm saying is valid for that. So if you take a nice massless rope, you pull. If I exert a force here, that is I am pulling this rope with, let us say, 5 newtons, the tension is equal to 5 newtons. The rope will pull me with 5 newtons. And then the rope will pull this fellow with 5 newtons. So what is that rope doing? It is pulling that other object with T, tension T. So we usually write it like this. So suppose I had one block and I have a second block, and I am now pulling this with some 20 newtons. It does not mean this is 20 newtons. But if this tension is T, this side, this rope is pulling this block with T. So how much is this force? T. But what about that block? This rope is also pulling that block. And what is that force? T. Okay. So if I have a long rope, this side the rope is pulling with T, that side the rope is pulling with T. So I hope that is clear. Tension is always a pulling force. What do I mean by pulling? Normal force is always a pushing force. Okay. So for example, floor is pushing. Floor is not pulling the block, floor is pushing the block. Okay. This inclined plane is pushing the block, whereas the rope is pulling the object. So it's pulling and pushing. If it turns out that you find tension is pushing, wrong. That means there is no tension. Because with a rope, how will you push with a rope? What will happen to the rope? It will have a slack, right? So that means the rope is not going to be able to push. So for example, if I had a rope like this and I try to push, the rope will end up doing that. So we call this a slack. So once I push it, I'm not going to be able to use the rope to push. Main forces, let's repeat. Gravitational force, always equal to mg on the surface of the earth. If you go very high up, this number will change. Okay, m into 9.8 or 10. More exact answer, we should be using 9.8. But many times we'll just use 10 for calculation, no? Otherwise it's much more difficult. 7 kg into 9.8 is too much work. 7 into 10, 70, very easy, right? So we'll use 10. In the exam, if they say use G equals 9.8, don't use 70, write 7 into 9.8. Now the second important thing is contact force. This is contact. Two parts to the contact force. Right now we'll only focus on frictionless surface, smooth surface. So whenever we say the word smooth, we mean frictionless. Okay, smooth means very little friction, but we will use it as if it is frictionless. So in an exam, if they say there is a smooth table, what does that mean? No friction, which means this is not there, which means the only force is perpendicular to the surface. Okay, so normal force, it's a pushing force. This has to be a pushing force. Tension is what a rope is going to exert on a block. That is called a tension force. The rope itself has some tension. It is basically pulling on this side, it's also pulling on that side. So if on this side the tension is 5 newtons, on that side also the tension is 5 newtons. Okay, so these are the 3 important forces. But are these the only forces? No, there are many more. Like for example, there is spring force. What else? There are electric forces. Okay, so there are electric forces. There are magnetic forces. There are interatomic forces that we'll need to deal with. Now, these are all additional forces that we'll come back to at some other point. Right now, we won't deal with all this. We will just focus on gravitational force, normal force and tension. Later, we will study friction and spring force. Okay, now with these 3 forces, there are quite a lot of things that you can do. Let us look at how to apply this to a bunch of different types of questions. Now, let us look at a couple of examples. So, for example, if I had a block that I'm going to place on a floor like this, let's assume it's a smooth floor. And let us say that this was 8 kg block. What are the forces acting on this 8 kg block? First, I will separate this block out. We call this the free body diagram. So I will say I have an 8 kg block and there is one force which is the gravitational force. How much is the weight of the object? 8 into 10, 80 newtons. And then there is a normal force. It is always a good habit to start by saying it is N. Don't assume N is 80. In this question, it will turn out to be 80. Next question, it won't be 80. So it's important to keep that in mind. So there is a normal force N. Now this is the floor and it is at rest. This object is at rest. So usually we draw the floor like this, just to say that this is fixed floor. Okay, so this is fixed to something on the ground. Now what is the acceleration of this object? It's not even moving. It's going to be at rest. So what is the acceleration of the object? 0. Okay, A is equal to 0 meters per second square. Always remember, only draw forces touching the body. Now, have I marked all forces on the body? Yes, because it's a smooth floor, no friction. Now, net force must be 0 because acceleration is 0. Now, remember Newton's law. F equals, net force is equal to mass into acceleration. 8 into 0, 0 must be equal to the net force, which is N minus 80. Therefore, N is equal to 80. Remember, it was not 80 because normal force, opposite of it. People sometimes call this normal reaction. Very bad word. Okay, normal reaction makes it feel like it is reaction to 80. It is not reaction to 80. Reaction to this 80 is on the earth. The earth's center, you are pulling the earth's center. Okay, this object is pulling the earth's center. That force is the reaction force. Who is exerting this? The floor is pushing it. The reaction force is on the floor. Okay, so this object pushes the floor. Just to kind of make you sure that this is not always 80, let us take another example. So here I have a lift, elevator, lift. Now this lift is going up. Again I have this 8 kg block. The lift is going up, let us say, with an acceleration of 2 meters per second square. Now I am going to draw the same diagram, free body diagram. Free body basically means you don't draw this floor, don't draw the lift, just separate the body as if it is in space. But mark all the forces on the body. What is this force? 80 newtons. What is that? That was the weight. And what is this force? N. But now, if the lift is going up with 2 meters per second square, you think the block will remain at rest? Or is it also going up? It's also going up. Well, how can my hand go up and the chalk remain there? So this block goes up along with the lift. So if the lift has an acceleration of 2 meters per second square, what is the block? 2 meters per second square. So this guy's acceleration is 2 meters per second square. Now remember, I have to still write F equals ma. So if I write F equals ma, start with ma. ma. So 8 into 2. What direction? Up. Therefore, mass into acceleration is up. So net force is up. N minus 80 is 16. 8 into 2, 16. So what is N? 80 plus 16, which is how much? 96 newtons. Is it equal to 80? Is this equal to 80? No, right? Different. There it was 80. Here it is not 80. Okay, let us take another example. Exactly the same kind of lift question, but now what happens is that we have the lift going down with 2 meters per second square. Lift is going down with 2 meters per second square. This is an 8 kg block. Same free body diagram. Always draw the free body diagram. Now do you think because it's going down, is the floor pulling the object down or is it pushing? Think about it, it's a tricky question. The floor is going down. So is the floor pulling the 8 kg? No, right? When I'm going down also I'm pushing up. When I'm pulling this object up and I'm taking it up, also I'm pushing up. So normal force is up. It can only be pushing. Weight is 80. But acceleration, what about the acceleration? 2 downwards. Mass into acceleration. 16. Downwards. Should I say n minus 80? No. Now because it's downwards, so I'm going to say 80 minus n. I hope that is clear, right? So therefore, what is n? 80 minus 16, which is 80 minus 10 is going to give me 70, 64. Right? So here it is 64 newtons. Do you understand? N is not equal to mg. Sometimes it is. Here it is equal. But sometimes it is not. And therefore we must be very, very careful when you're solving problems. Keep it in mind that sometimes n may be equal to mg, sometimes n won't be. You have to find it out in each case. Here the object was at rest. Here the object was accelerating up. Here the object was accelerating down. If the object was moving with uniform velocity, acceleration is 0. So it will behave like this. If the object was accelerating downwards, that means you will have to take downwards. So that means you are doing 16, but you are writing 80 minus n. If the object was accelerating up, you are writing n minus 80. So little bit tricky, but you have to think about it. It's an easy kind of an idea, but you have to think about it. Now, there is a special word people sometimes use because you can actually place a weighing machine here. We call this apparent weight. So suppose I stand on a weighing machine shows some reading. What is it actually showing? It's not showing my weight. What it's showing is how much force I am pressing the weighing machine with. Weighing machine has a spring, you are pressing that spring. And then when the spring gets pressed, the reading starts to turn, right? Basically the marker starts to move. Now, what it shows, it's basically calibrated that you don't even have to stand. No, you can press the weighing machine, anyway it will move, right? So now usually if I keep a weighing machine here, and so I'm standing on the weighing machine, this fellow pushes it with how much force? N. Why? Because the weighing machine, I have drawn how much force does the weighing machine exert on this fellow, but if you draw the weighing machine, there is also an equal and opposite force. So if this is 80, how much is this? 80. So what will this show? 80. It will show 8 kg, but that's because 80 divided by 10. But what it is reading is 80 Newton. So now the weighing machine is saying, hey, your weight is 80 newtons. But if I keep the weighing machine here, weighing machine has to push this fellow how much? 96. Therefore, this fellow will push the weighing machine with how much? 96. So what will the weighing machine show? 96. So when the lift is going up, your apparent weight has become 96. Apparent weight does not mean your real weight. This is your real weight. Apparent weight is what the weighing machine is showing. But why is it showing more? Because weighing machine has to push you more. Why does it have to push you more? Because not only does it have to compensate for the 80, it has to also take you up. So it has to exert the 2 into 8, 16 more than 80. So 16 plus 80, 96. Is that okay? Now if you come here and you have a weighing machine and you're standing on the weighing machine and the lift is going up, then you are pressing this weighing machine with 64. So it feels weightless. Not weightless, you have less weight. Okay, now the question is, suppose instead of 2 meters per second square, this lift is coming down really fast. What do you think will happen? Think about it. If the lift comes down with a very high acceleration, let us say 12 meters per second square. So now I have a lift and it is coming down at 12 meters per second square. This is 8 kg. If you do the calculation, what you will find, same question, except instead of 2, I'm going to put 12. So I'm going to say 8 into 12 downwards, and then I'm going to say 80 minus n. If I calculate this 8 into 12 is how much? 96. So n turns out to be minus 16. This is weird. Why is it weird? Because this means the weighing machine is pulling you. That's not going to happen. What will happen instead? So why this is not working out as we thought is because if I take this object, if I'm pulling it down slowly, it is stuck, which means there is a normal force. But if I come down very fast, notice when I'm coming down very fast, think about it. I'm going to show it to you. Again, you can see this in slow motion. Okay, if I move this very fast, did you see that it's separated out? Right? So that separation is because I am moving too fast. I am moving with more acceleration than g. The maximum acceleration this guy wants to come down with is g. So if I go at greater than 10 meters per second square, actually greater than 9.8. If it is greater than g, then this will start to separate out. If it was exactly g, also you won't have any force. So it feels weightless. Some of you may have had this feeling. Some of these theme parks, there is this boat, big boat. You sit on that boat, and as the boat comes down, everybody is shouting. Why? Because when the boat comes down, you feel weightless. You feel like the normal force, actually what you feel is that the normal force has reduced. Okay, so we call this, this is wrong. So the normal force is 0. If you found that normal force instead of pushing turns out to be pulling, it's wrong. Normal force can only push. Okay, so what is happening is this just separates out. So if it separates out, how much force? 0. So that is the answer. Okay, but then there is a difference because when they separate out, this 8 kg has only 80 newtons. This is 0. That means it has an acceleration of 10, whereas the lift has an acceleration of 12. So they start to separate. So lift and block do not move together. So I hope this is clear. So this is one application of how we use normal force. We have also learnt a very important idea, which is apparent weight. When we get to problems, you will use this a lot. So when the object is moving up with an acceleration, you place a weighing machine. The weighing machine is pushing more, which means the object is pushing the weighing machine more. So that means your apparent weight is more than your real weight. Similarly, if the object is coming down, when the lift is coming down or the object is coming down, then it is pushing less. So apparent weight is less. But what is apparent weight? So let me write that here. Apparent weight is nothing but the normal force in this case. Sometimes it might be the spring force, but many times it is just the normal force. Real weight is not normal force, it is mg. They are very different. Okay, so now we have understood how to use normal forces. Let us learn to use a little bit with tension.